Hey guys, this is Dex Yankee Oscar 3 Hotel Echo X-Ray. For the last couple of days, I was playing with a new software that I found. It's called uSIMMICS. The latest version is 5.8, freely available. An radio frequency simulator, excellent GUI, excellent functionalities. I found it to be very nice. You can download it from here. Previously was named Quite Universal Circuit Simulator, if I remember correctly. Now they've renamed it and they've changed a little bit the GUI, and you can download it from here. You would end up with an archive. You just unzip it, and in the bin directory you will find the executable for the uSIMMICS 5.8. Why is this a very nice addition? Because well, it's free first of all, and you will get to have also EM simulation. You can create filter synthesis. You can create all kind of. You have all kind of RF calculators that you can actually use. So I was looking around and I haven't found any, like, I don't know, real or any in-depth type of tutorials. So I've decided to share with you what I was able to find out in the last couple of days. So, after you are going to start it, you will end up with this kind of canvas, and you will have access to the components, which first of all you will need sources. You will need AC power source, which is, in this case, you can add only one, and you can add a ground connection. But if you need to do scatter parameters like 2-1 or 1-2, you will need two ports. So that would allow you to define two ports, P1 and P2. If you need only S11, you can end up by adding only a 50 ohm resistor here, and it's fine and dandy. The simulation will work without a problem. In fact, you can do that. Another thing that you can add, so this is, I would say, this is the basic setup to begin with. You add two ports. Now those ports, you can define the power, you can define the impedance, you can define a frequency, but this is something that we are going to discuss a little bit later, because you can in the simulation you can change that. Now you can do all kind of stuff. For example, if you would like to see a transformer that would adapt the impedance from 50 ohm to 200 ohm, you can do that. You just change here the impedance, the output impedance to 200 ohm, and just run the simulation. We are going to leave it on 50 right now. And the easiest thing that you can actually simulate is a transmission line, which in our case it's a microstrip line. You just take it, put it here. You are going to add some wires. They do have a little bit to work on on the GUI. You know, it's a little bit clumsy, but 100% usable. It's not a problem at all. So not a problem at all. Just give me 1 second to put this wire, because my OCD will strike. So okay, so we do have a substrate. We do have a strip line with a width of 1 millimeter and a length of 10 millimeters, which is fine and dandy, but we do not have any definition of the substrate. So another thing that you will have to do before simulation, you are going to take a substrate and what you want to do. We are going to the simulation and you are going to look for an S-parameter simulations. We are going to drag those here just put it in a corner what we can. And first of all, let's define our substrate. I'm going to run with FR4, which is around 4.5, between 4.2 and 4.6. I've seen various values. The substrate height in my case, for example, for something that I'm going to show you, this is something that I've been experimenting with. I hope you can see it. Yeah. So you have only one side PCB, one side copper clad, and this is some copper foil. Yeah. So that particular PCB is 1.2 millimeter, and the copper foil that I'm using is 60 microns. Yes, it was measured. So yeah, you can go out and say, okay, the backside will not be metal, but it will be air. If you have only some copper foil on top, like for an antenna maybe, you can have a small Yagi on the PCB, but it wouldn't be very nice to have a back plane in case of that. Yeah, you will have to define your own. So I will leave it like so. After that, we said that okay, we have this substrate, we've defined our PCB, but I would like also to go to the S-parameter and say, okay, I don't want from 100 megahertz. I would like from 1 gig to up to 3.5 gigahertz. Okay. Now you can define the number of points here. I'm putting around 250. If you are going up with it, you are going to have a longer time of simulation because you got a finite type of an MOM type of simulation. So that would basically put a little bit of overhead. So after this, we can run the simulation as it is, okay? But you will see that's a good exercise. So we have a substrate of one transmission line of 1 millimeter with a 10 millimeter length. So if you are going to press, either we are going to tools and simulation and click simulate. We are going to have to save it. Let's call it test. Okay, you will see that the loss here it's quite substantial. Yeah, it's quite substantial, and on the Smith we are quite away from the actual 50 ohm target. Yeah, if we are going to take a marker and we are going to put it, I don't know, at the beginning, which is 1 gig, that will give us around 56 ohms. And if we are going to the end of it, which is 3.46 gig, it's 100 ohm. This is because our transmission line, based on our substrate here, it's not correctly calculated, it's not correctly dimensioned. Yeah, you can see also we are having some losses here. At 3 gigahertz, we are having around 0.5 dB, which is quite a lot. Now, on the other hand, this is very easy to do. You are going to tools, and we are having, like in KiCad, for those who are running KiCad, those type of calculators are available. So we are having a transmission line calculation that it's either Control N3 or you are going to tools and transmission line calculation. Okay, so window would pop up here. You can redimension it a little bit if you like. Now, our maximum frequency is how much? Let's say 3.5 gigahertz. This will not have a very big impact on the transmission line itself, but it will, the frequency that is, but it will have a very big impact if you would like to make a quarter wave lambda transformer. So that will have to be dimensioned for a certain frequency, of course, because it will have to be calculated for a certain frequency. So right now, doesn't really matter, but let's go with the worst case scenario, which is 3.5 gigahertz, our maximum frequency of interest, and we are aiming for a Z0 of 50 ohms. Yeah. So that would give us, before that, we will have to define our substrate again. So in our case, we got FR4, we have the standard resistivity of copper, and we are having the T parameter, which is the thickness of the stripe is 60 micrometers, and the height of the substrate is 1.2 millimeters. After we are going to define that, you are all good to set, you are all set to go here. So we are aiming for a 50 ohm type of impedance, standard impedance. So that will tell us that for a 50 ohm impedance, we are aiming for 2.19 millimeter. So if we are going to go here and we are saying 2.19 millimeter, the length is not necessarily important right now. It would be more important if we are trying to do a phasing line or a delay line. Yeah. Now we are going to leave it at let's say 20 millimeter. What it will happen? The losses in the transmission line will go up a little bit, but the impedance will be the same. So the losses are going to go up because you got some losses in the copper itself. Okay. So if we are going to run the simulation again, and this time I'm going to press F2 because it's easier, you would see that we are dead center in the 50 ohm on the Smith chart. The losses are almost neglectable. Yeah, we are having less than I don't know, something dB, yeah, and it's kind of the same all over the place. Okay. The impedance match on the return loss, of course, it's theoretical. You will not have something like this in reality, but it's good to see. We're having minus 114 dB for the return loss, which is not. If you are going to have something around minus 24 to minus 40, be happy with it. It's all good. But again, it's just a simulation. You are aiming a lot for this because in real life you will not have the exact 2.196 millimeter wide. You will vary a lot. If you are not going to go for like an impedance control type of substrate, your substrate on the FR4 will vary a lot. So 4.5, between 4.2 to 4.6, I've seen a lot of values that were vehicular. I didn't measure it for what I have. Those are kind of the numbers that we are in. So this is almost a perfect match. We are spot on in the Smith chart here. And that will allow you to see as 50 ohm, dead on, yeah, which is good. Now, that was not that impressive, right? So that was not that impressive. So if we are going to delete those, because in the end it's easier to have a clear screen. Okay. So the easiest thing to do with a microstripe is to have a notch filter. Okay. So if we are going to have go again to the transmission line, we are going to say, okay, we have a microstrip open. Let's see. This is not necessarily the case. So let's see the microstrip line here. Or we can go, we can, let's say, microstrip. Let's put it on. Okay. Nah, let's put it on microstrip line. A simple microstrip line here because it's easier to see it like this. Yeah, it took me a little bit of time to take a decision, but let's put it like this. So if you would like to have a notch, what we know is that a notch will be a quarter wave stop, open stop. A notch will be a quarter wave open stop at the frequency of interest. So let's say we would like to have a notch at 2.4 gigahertz. What we also know is that we would like to see an angle, a deviation of phase inversion of 90 degrees, because you have 90 degrees to go and then you get a full reflection because you have an open notch, you have an open stop, sorry. You have an open stop, you get a full reflection. So you have 90 degree first and then you have 90 degree again, which would give you 180 degrees. So by the time that the signal is going down and back because of the full reflection, it's open, yeah, you would get a 180 degree out of phase signal that will cancel out the frequency of interest. Okay, so let's say I would like to have a 90 degree type of phase shift, yeah, that would give us a length of 17-ish millimeters. So the width is 219. We can actually take it from here because it's the same strip line. So 2.19. The length, we can see for 90 degree type of phase shift, we will get around 17 millimeters, so 17 millimeters of length. Okay, that would give us that. Let's rotate this one a little bit. Okay, so we've put our open transmission line, which is basically a stub, in the simulation. If we are going to press F2 or go to simulation and simulate, you will see that we are getting a notch like we've simulated at 2.4 gigahertz with a depth of minus 42 dB, and that would give us a very good rejection. Okay, so S21 is the transmission from port 2 to port 1, which is, it's kind of basically the same because we are having a symmetrical type of thing. Okay, so if we are going to delete those, the impedance was shifted, of course, but that's not the point. If we are going into tools and we are saying create EM layout, we are going to get this type of thing where we can actually create our own microstripe type of, I don't know, let's call it infrastructure. Yeah, you can add various stubs, you can add various bands. You can put it like this, and after that, everything would be microstripe. You can add it, and you have you would end up with metered bands and etc. So you can have that, and after that, let's leave our stub here, and after that you can actually go on and hit F2, and it will create also simulation of your strip. Yeah. What is the difference, you would say, between having this simulation and having that simulation? Well, that it's quite easy to understand, because when we are having something like this, you can also add elements in the mix, and you can simulate for certain, I don't know, topology of filter or whatever you're trying to achieve. So if you are going to hit F2 again, the simulation will take some time, because you will see in the back here, everything is divided in microgrids that would be applied some mathematical formulas on it, and you would end up with a response and a mathematical simulation of what you are trying to achieve. That's why it will take some time. As and this is, truth be told, this is directly connected with how big your filter is from the, or whatever transmission line you are trying to achieve, stubs, etc., from the physical point of view, because everything will get divided in smaller pieces, and everything will be applied to that particular small piece from the whole system itself. The simulation will take some time, but you are able to run the simulation not by modifying the schematic here, yeah, but you can also add finite elements along the line, yeah, in your simulation and simulate it. You can save it, you can do whatever you would like to with it, and you can have your simulation. You can even add ports, RAM connections, etc. Yeah. So after this simulation, hopefully will be done. We will have some results. We will have some stupid results. Don't expect something magical. Yeah, it's to be expected. Yeah. It was just a stop there, so added totally randomly. So you will end up with another type of response because you've modified your system. So you're not tied directly to this particular schematic. What I would actually, I would actually do, I would put at least a strip line here with 2 ports, and I would define my S-parameter and my substrate, because in the end, if you are running, you can do it without any of those parameters, but your system would be simulated, I do think, against a Rogers substrate, which would not fit your need. Yeah, that's why it's better to go from a schematic in which you define all the simulation parameters, and after that you can go on and modify your PCB and create various things in it. Yeah. You can also, for example, let me see if I can do it here. Sources, not sources, where was it? System components, no. Lamp components, yeah. We can even get a ground, so this here, it's a ground, okay? This here, it's a port, yeah? You can add it directly from the transmission, from the sources. You can go out and you will have another port here, and you can add another port, for example. Yeah, you will have the simulation ports here. It's no need because we are already having 2 ports here. But here we've grounded the stub, yeah. And if you feel so inclined, we can actually run the simulation again. Let's close that. Let's run the simulation again. Probably it will take a little bit of time, but you will see other type of response in the S21 and S11. Yeah, so we have totally different type of response. The frequency was shifted to about 2.9 gigahertz, so that is the result of adding this particular stub here and adding ground here, yeah, which is all. So this is something that can be done relatively quickly with relatively less effort to synthesize filters or transmission lines. And I can tell you that I've made some tests, and it's working 100% accurate from my point of view. There are other things that are nice here. It's about, for example, you can go on and You have, I showed you the transmission line calculator, sorry. So you have this for various transmission lines. You can even have arbitrary cross sections, so you can define your own type of strip. Yeah, you can define your own strip, and you can put it here, and you would get the necessary data out of it. So you have a lot of transmission line. You have a slot line, which you can use. Of course, with the slot line, you would need to go higher frequency because it's totally dependent on the frequency. But you have also a rectangular waveguide, which is a very nice addition if you're asking me, which I don't think it's available in KiCad. So you have various transmission lines here. Yeah. What you also have is you can also have a matching circuit to be synthesized. You have, let's see, attenuator synthesis. Yeah, you have it here, various topologies. You can actually go out and see how it behaves, the wattage needed, etc., etc. I find it excellent, very useful. And now the cherry on top is the filter synthesis, which you can actually put it. Let's see if we can go out and delete those. Let's go with, say, I would like an end-coupled transmission line of order 3 between 2 and 2.1 gigahertz with an impedance of 50 ohms, 4.5, 1.2, 60, and let's calculate. The result is successful, and it says I've put it already in the clipboard, and you can press Ctrl and V, of course, like any paste, or you can go on and say paste, and you have it here. Okay, so we can delete that. So we have everything here along with the generated filter. If we are going to simulate it, oh, sorry. Okay, yeah, that's quite good because the name is substrate 1, not substrate 2. Okay, let's see. And we are having a filter here. Sorry, we are having the filter here, which is a bandpass filter as expected, and I would expect to be as close as 50 ohms in the pass band, which would give us around, so 2.04 is the closest. Now the insertion loss on this one is approximately minus 1 dB. I would expect to be in that band. In reality, probably it will be a little bit higher than that. Now you have this filter. What you can do is create EM layout, and it will lay it out for you in a very nice way. Yeah. You have the port, you have some added capacitance here of 0.46 picofarad. That would give us around 465 femtofarads, which you will have anyway. So, but you can see here that are gaps between transmission lines. And you can also simulate it. Again, by going and simulate this, you would get a, let's say, more brief type of information, not with the Smith charts and everything. But you can simulate it from here, or you can simulate it from the schematic. It's kind of the same thing. It will take some time because, as I said, you see, it's already divided in various bits and pieces, and I don't know if this MOM simulation is directly connected with the processing power, or it would be something else. I really don't know if it's using Octave for this simulation underneath, so probably Octave would be able to use some kind of acceleration if it would be available, like CUDA cores maybe, or something else. But let's wait for the simulation to finish, and you will see the results hopefully rather soon than later. Okay, so we have this, which is a little bit different, as I said. Yeah, which is a little bit different because the simulation is starting from 1.9 gigahertz from 2.2. Okay, so I would say that it's a very nice tool to simulate, learn, experiment, and then put it into practice and see how it behaves, because it allows you to see at least big mistakes before you put it down. For me, it's a very nice tool, and I hope you enjoy it. Thank you for watching this, let's say, tutorial, if you like. It was more like a very crash course on using the uSIMMICS 5.8. Kudos to the ones that created this particular piece of software. Very nice. I loved it. And I hope you enjoyed it too. This is Yankee Oscar 3 Hotel Echo X-Ray Dex directly from his shack, and I hope you enjoyed this clip. See you guys, all the best. 73.